Okay, here we go. How you doing today? Today we're talking about rates of change, tangent lines, and sensitivity. What you'll be learning about is tangent lines, slopes of curves, instantaneous rate of change, and sensitivity. I think I might let that go to the next video. We'll see if we get to it or not. But the tangent, and why we learn this is the tangent line determines the direction of a body's motion at every point along its path. So let's see, we have a warm-up to do. So if you guys would pause your video and do the warm-up here, you have 1, 2, 3 through 7, right? 1 through 7 to do. Okay. All right, now that you had an opportunity to get that done, so checking your answers over here, we've got just some simple exercises to find delta x and delta y in the first two. We have the slope, finding the slope, and then writing lines that are perpendicular or parallel. So we have those two checked off. Number 5 is 4/3 x plus 8/3. Number 6 is a line parallel would be negative 2/3 x plus 7/3. And then just setting up the slope, solving for b when you know the slope is 5/3 to get b is equal to 19/3. Okay, so in this next section, first we're going to begin by talking about average rate of change. And it's a quantity over a period of time, quantity changing. So the average rate of change of a quantity over a period of time is the amount of change divided by the time it takes. Makes sense. If you drive 180 miles in 3 hours, you drive 60 miles per hour. So in general, the average rate of change of a function over an interval is the amount of change divided by the length of the interval. And then the average rate of change can also be thought of as the slope of the secant line to a curve. And if you see, here's the secant line. So a secant line passes through a couple of points, and you get an average slope on that interval from A to B. So let's take a look at finding the average rate of change. So when we're finding the average rate of change for a graph, finding the average rate of change of this parabola on the interval from negative 2 to 4, and remember that these are x intervals. So we look for, here's our negative 2 on the graph, and then we go to 4. Oh, I think I marked 3 there, but it's 4. Here. Anyway, so what we want to do in this is we want to just say f of 4 minus f of negative 2, and put that over 4 minus negative 2. So it's going to be 4 plus 2, right? So what we have there is, and I've already gotten these worked out ahead of time, so you can see we have 27 for f of 4 and 21 for f of negative 2. So we're just going to plug those in. So we end up with 27 minus 21 over 6. So we get 6 over 6, and we get a slope that's equal to 1. Now you have to see that I'm up a little higher here, and so it's kind of tough to see where it's going. It's not going to be a game of exacts. I'm just going to put 427 here, and then negative 221 here. So you can kind of see the line is increasing somewhat. That would give you the average rate of change from the interval from negative 2 to 4. Okay, so that's average rate of change. So tangents to a curve. In calculus, we often want to define the rate at which the value of the function y is equal to f of x is changing with respect to x at any particular x value, x is equal to a, to be the slope of the tangent line to the curve y is equal to f of x at x equal to a. Okay, so we see that at any particular value, x is equal to a, to be the slope of the tangent line at x equal a. Okay, the problem with this is that we only have 1 point. In this previous problem, we had 2 points, and we got the average slope. Here, we are only going to have 1 point, and our usual definition for slope requires 2. So what we're going to do is we're going to eventually look at a situation like this. Now, I'm going to do this informally first, where we're going to consider 2 points really close to one another on a curve, so close that h will go to 0, and it'll get so close that you'll be right on top of -1, 3 in this case. But so here's the problem. The tangent to the curve, we can kind of say, oh, it looks something like this, right? And it's going to look something like that. We could just take a guess at it. So it passes through just this 1 point here in that little neighborhood. Okay, so given y is equal to x squared plus 2 at x is equal to -1, find the slope of the curve and an equation of the tangent line. Then draw the graph of the curve and the tangent line in the same viewing window. I saved you a little trouble here and just put the graph on for you. Okay, and I calculated, I put the x into the function y is equal to x squared, and I got, for a function value, I got 3. Okay, so the first thing we're going to do is I'm going to use this kind of idea that I want to find the slope of the secant line expression first. So that's going to be f of -1 plus h minus f of -1. And that's going to be over h. And I have this little triangle here so you can kind of see where I'm getting this idea of slope from. This is the change in y here. And this, of course, is the change in x. Remember, you would take -1 plus h minus -1, and you would get just h. Okay, so slope of the secant line, and we're just going to plug into that then. I have the slope of the secant line is then equal to, the function is -1 plus h, and it's the quantity squared plus 2. And then that's the first part, brackets here. And then it's going to be minus 3. That's all over h. Okay. And so that's your expression. We could simplify this a little bit. So why don't we go ahead and do that? We have, this is going to be -1. Oh, here, sorry. I'm just going to write the same thing over again. So it's going to be 1 minus 2h plus h squared plus 2 minus 3. So I'm just going to simplify this expression over h. So it looks like I have 1 plus 2, 3, minus 3, which is 0. So then I have the expression, the slope of the secant line is equal to, I have the h squared, I'm going to highlight it here. This is what I'm going to have left. So all this other is going to cancel, the 1 and plus 2 minus 3, that's all going to be gone. So then I've got, I'm going to factor this. I'm going to put the h squared first, but just go h times h minus 2. So kind of flip things a little bit there. Over h, cancel the h's. So I get the slope of the secant line then is equal to h minus 2. Okay, here's the expression in simplified form for the slope of the secant line. Now, what we want to do is we want to take this then, the slope of the tangent line is equal to the limit as h approaches 0 of this slope of the secant line, h minus 2, which is 0 minus 2, and then it gives us the answer of -2. Let me make sure that we have this answered properly. So it says, write an expression for the slope of the secant line and find the limiting value of the slope as q approaches p. So what that would mean is if we take a situation like this, this would be our q point here, and we're moving it to p. This would be our p value. Okay? So now we want to write the equation of that line. So we would simply take the point and put it in point slope form with our slope. So we have y minus 3 is equal to -2 times x minus a -1, which is x plus 1. So we get y is equal to -2x minus 2 plus 3. So we have y is equal to negative 2x plus 1. And there you have it. There it is. There you go. Okay. Let's see if I can get a couple more examples in on this video. Okay, so what we have here is this idea of the tangent to a curve of y is equal to f of x. For the slope of a curve, the tangent at a point P, A, f of A down here, to find the tangent, we calculate the slope of the secant line through P from this point, the Q. And what we're going to do is we're going to make the h value that we're talking about, we're going to make that go to 0. Because we already have, here's our delta y, and here's our delta x is h. We want h to go to 0, which would take this point, Q, and it would drive it down closer and closer to P until it's right on top. And then we would have the tangent line instead of the secant line. Okay, so that's what we'll get here. So the slope of the curve at y is equal to f of x at the point P, A, f of A is the number m is equal to the limit as h approaches 0, the limit as h approaches 0 of all this, provided that the limit exists. Now the tangent line to the curve at P is the line through P with a slope, okay? Great, so the slope of the curve, these are different ways that we can state the slope of the curve. Y is equal to f of x. The slope of y is equal to f of x at x equal to a. We have the slope of the tangent to y is equal to f of x at x equal to a. We call it the instantaneous rate of change of f of x with respect to x at x equal a. Or we just say like this, and we recognize that's the slope at a. And the expression, this expression in the last one is called the difference quotient. And that again is the slope of a secant line. Okay? Then the normal line to a curve at a point is the perpendicular to the tangent at that point. The slope of the normal line is the negative reciprocal of the slope of the tangent line. So, using the previous example from example 2, we found out that the slope of the tangent line was negative 2. So then we know the slope of the normal line is then going to be 1/2 because it's perpendicular to, the normal line is perpendicular to the tangent line. So if I draw this line, okay, going through this point, okay, this is the normal line. Okay, so then to write the equation for this, we would have the equation would just be y minus 3 is equal to 1/2 times the quantity x plus 1. And we could simplify that to 1/2 x, and that would be, if we distribute, we get 1/2 plus 3 or plus 7/2. Okay. Okay. There's the normal line curve. And then we have a problem with velocity, and that's revisited here, where we have the function 16t squared is an object's position function. A body's average velocity along a coordinate axis for a given period of time is the average rate of change of its position. Its instantaneous velocity at any time t is the instantaneous rate of change of position with respect to time. So it's like when you look at your speedometer and you see it says 65 miles per hour, then it's instantaneous. There's not a change in time associated with it. So what we're going to do with this is that we're going to look at an equation for a free fall on Mars is given by the position. The position is equal to, is S is equal to, S is the position, 6.1 t squared. So with that 6.1 t squared then, we have where t is in seconds, assume a rock is dropped from a 100-foot cliff, and you want to find the speed of the rock at t is equal to 3.5 seconds. So with the instantaneous velocity, I'm going to use, instead of functional notation, I'm going to use an s here for the function. And then I'm going to say the limit as h then approaches 0 of s of 3.5 plus h minus s of 3.5 over h. In this case, the a value is 3.5. Okay, so I get then the limit. So this is our instantaneous velocity. The limit as h approaches 0 of, now I'm going to put the function values in, but I'm going to leave the 6.1 out front. And then I've got 3.5, since it's just going to be squared then, right? So, well, I'll put 3.5 plus h squared, I guess I could put that in there, minus s of 3.5 would just be 6.1 times 3.5 squared all over h. So then that's equal to the limit as h approaches 0. I'm going to leave the 6.1, and then I get 12.25 plus 7h plus h squared minus, I'm going to put the 6.1 in again, and I get 12.25 when I square 3.5. Okay, so then that's all over h. And then we have the limit as h approaches 0 of, I'm going to take the 6.1 out, and so that leaves me with 12.25 plus 7h plus h squared minus 12.25. That's all over h. Cancel the 12.25s. And then we get the limit as h approaches 0 of 6.1, and I'm going to do some factoring here. So I have 7h, which I'm going to factor an h out here, and get 7 plus h, and then that's going to be over h. Canceling the h's, then so I get the limit. I can just go ahead and take the limit now. 6.1 times the quantity 7 plus 0. And if I multiply this through, remember you have units on the top and the bottom. The units on the top are feet, and then we have seconds. So we get 42.7 feet per second. And that's how fast the object, what's the object? A rock. The rock is dropping at 3.5 seconds. So there's a couple of more examples on here, but I'm going to have to stop the video and I'll pick back up with the remainder of the lesson. Have a great day, and I'll see you when I see you.